Hi, everyone. So how many solutions can a system of equations have? We've seen nonlinear systems with zero solutions, where the empty set was the solution. Remember the circle and the line? Remember that problem? We had the empty set as our solution set. Okay. We've seen two solutions, like the two parabolas, right? Mhm. And we've seen three solutions, um, like in the case of that first problem we did, where we had the line and then this snake, three solutions. Well, we can have infinitely many solutions for that matter. We can a nonlinear system can potentially have any whole number of solutions, and it can have infinitely many solutions. Look at this: y equals sine of x and y equals 0. Basically, we're solving sine of x equals 0, and the y-coordinate is 0 at those points. We're basically finding the x-intercepts for the sine wave. Let's do that. We have y equals sine of x, our good old sine wave, and we have y equals 0. I guess I should change the step size to pi over 2. All right. So we have zeros at every integer multiple of pi. So at 0 and at pi and 2 pi and so forth, also negative pi, negative 2 pi, and so forth. We have infinitely many intersection points. The sine wave had infinitely many x-intercepts. So the system here had infinitely many solutions corresponding to these intercepts. Oh, by the way, a couple other notes. What if I have y equals sine of x over x? This is a famous guy in calculus. Now, this guy has the x-axis as an HA, as a horizontal asymptote, and this graph actually crosses over its HA infinitely many times. Remember, there's nothing in principle that stops a graph from touching or crossing over its own HA, its own horizontal asymptote. We don't see that for y equals 1 over x. This guy avoided his HA, but y equals sine of x over x crosses over its HA infinitely many times. And again, we have infinitely many solutions to the system. Again, it'll be at the integer multiples of pi, except at x equals 0. When x equals 0, there's actually a hole up here. There's actually a hole at the point 0, 1. And in fact, this explains part of why the derivative of sine of x is cosine of x, this hole on the graph. Anyway, let's try something else. Here's y equals sine of x. Here's y equals sine of x. Oops. I'm basically recoloring the graph, but if you consider this group of two equations as a system of two equations, every point on the sine wave is an intersection point. So the system has infinitely many solutions corresponding to every point on the sine wave. All right. Now, I have a question for you. What if we restrict ourselves to linear equations and linear systems? So think about the xy plane, okay? Think about Desmos here, the xy plane, all right? Now think about lines. Think about lines. I'll go back to the regular coordinate systems here, all right? The regular scaling, right? Think about lines. In the plane, in how many points can two lines intersect if you're dealing with the plane? In how many points can two lines intersect? Well, there are only three possibilities. They're either no intersection points, one intersection point, or infinitely many. Infinitely many. So let's think about this. Okay. How do two lines normally intersect? Well, here's a line, okay? There's one intersection point. It's like an X, right? So of course, it's possible to get one intersection point between two lines, and exactly one solution for a system of two linear equations in two unknowns. But how can you get no real solutions? How can two lines never intersect in the plane? You take this line And how about a parallel line? That's different. Hint, hint. How can I get infinitely many solutions? It was similar to what I did with sine of x on Desmos. Here's a line. Well, draw another line right on top of it. Same stupid line. Just like we had same stupid sine wave, here, same stupid line. Infinitely many points. A line and its copy. All right. So again, if you have a linear system in two space, basically, right? How many solutions could you have? Well, you could have no solutions, like here, if you have different parallel lines, in which case the system is inconsistent. You could have exactly one solution, which corresponds to the intersection point between non-parallel lines, or you could have infinitely many solutions, where you have coincident lines. Same stupid line, same stupid line. So if you're dealing with the plane, there is no way that a line, which by definition is a straight line, okay, there's no way that two lines, meaning straight lines, can intersect in exactly 2 points or exactly 3 points. That cannot happen. They have to intersect in either no points, 1 point, or infinitely many points. Same stupid line. So this suggests now some possible special cases. For example, solve this system. You don't even have to show any work. Solve the system. X plus y equals 2, x plus y equals 1. Are there any ordered pairs, x comma y? Do we have any pair of real numbers whose sum is 2 and whose sum is also 1? Can you think of two numbers that add up to both 2 and 1? Real numbers? I can't. Solution set is the empty set. We have no ordered pair x comma y that will satisfy both equations. Graphically, what happens? Graphically, how would you graph these? You can think in terms of intercepts or slope-intercept form. Let's think intercepts. What are the intercepts for this first line? 2 comma 0 is the x-intercept. 0 comma 2 is the y-intercept. So here's the graph of x plus y equals 2. What about the graph of x plus y equals 1? That has intercepts 1 comma 0 and 0 comma 1. X plus y equals 1, a different parallel line. These two equations correspond to lines that are different parallel lines. How many intersection points? 0. The empty set is the solution set. What if you try to do this using algebraic mechanics? Now, before, I mentioned how it was easier for us to add than to subtract, but I think we can hack this. What happens if we subtract these two sides from these two sides? What happens? On the left side, we get 0, right? This minus all this is 0. 2 minus 1 is 1. So here's the logic. If this system has a solution, then the solution must solve 0 equals 1, meaning 0 equals 1 must be true. Now, hold on. If the system has a solution, then the solution must solve 0 equals 1. Somehow, 0 equals 1 would somehow have to be true somehow. No. Think about the contrapositive. Remember the idea of the contrapositive? The contrapositive of if P then Q, contrapositive of if P then Q is if not Q, then not P. Switch and negate. What's the contrapositive? Do this in blue. What's the contrapositive of this statement? Well, if 0 does not equal 1, and isn't that the case? Oh, how about this? If the solution does not solve 0 equals 1, then the system has no solution, no real solution. no real solution. Oops. All right. If the solution does not solve 0 equals 1, well, nothing solves 0 equals 1. 0 equals 1 is always false. Unless you have a weird number system, 0 equals 1 is always false. Then the system has no real solution. It's the logic. This is true from our mechanics. Therefore, the contrapositive is true. Hey, 0 never equals 1. The system has no real solution. All right, so 3 different approaches, right? Just sort of your mathematical sense way. The sum cannot be both 2 and 1. What is the solution to a system? It's got to solve all the equations. Also, if you consider graphs, no intersection points. Also, if this is going to be true, then somehow 0 has to equal 1. Somehow, and that can never happen. Empty set. That's your solution set. What about something like this? How many solutions does this system have? If we covered this up, if we just had the top 2 equations, there would be infinitely many solutions. Same stupid line, right? Y equals x plus 2 and y equals x plus 2, same stupid line. Infinitely many solutions. But if you throw in this requirement, this equation, remember, a solution to a system has to make all 3 equations true. This third equation is never true. So if you throw this guy in, empty set, right there. If you throw in more equations, it's like throwing in more conditions. You can never expand the solution set. You can only keep it the same or contract it. So here we start with this. Infinitely many solutions, right? Infinitely many points on the line, right? Infinitely many points along the line. Throw in the second equation. Well, it's the same stupid line, right? You still have infinitely many solutions. But then you try to throw in this third equation. That kills it. So this one weak link in the chain breaks the whole chain. Empty set. Next up, how can we consider graphs of linear equations in 3 space? It's no longer lines. What are they going to be? Next time.